Hi everyone, welcome back. It's your favorite host, Haluk here. Right, so we're going to continue with the last lecture of Hang. Hang, here you go, please.
Thanks for the introduction. This lecture, I'm going to present a proof of Conca's power of isomorphism in some simple cases. The plan is the following. So we are first going to say something about the case of Rn, the simplest case that is essentially claiming that the K-theoretic index is just the Bott generator under Fourier transform. And then I'm going to spend most of time on the case of complex semi-simple Lie groups, which is due by Pennington-Kleiman. And I will say a few words about discrete series and the case of SL2R. That is the plan for today. So let us recall the Conca's power of isomorphism says that for an almost connected Lie group G and the maximal compact subgroup K, we have a Riemannian manifold created by G mod K. It has a G invariant metric given by the Killing form, and not necessary, but here we are going to assume M having a G equivariant spin structure, and therefore one can create from every irreducible representation of K, one can create a homogeneous vector bundle over M and twist it with the canonical Dirac operator associated to this spin structure to have this dV, and one can take the K-theoretic index, which lands in K-theory of the reduced group system algebra, and the Conca's power of isomorphism states that this is an isomorphism of abelian groups. And our aim today is we are either assuming G to be a complex or a real semi-simple Lie group, and we would like to apply the Fourier transform on G to study actually the Fourier transform on the reduced group system algebra of G to study how does the image of the equivariant index of this twisted Dirac operator transformed into, and using this method will allow us to find to understand better the relationship between K-theory of group system algebras and representation theory of semi-simple Lie groups. And as before, we are going to use this G hat T to denote the subset of all tempered representations of G. And we are going to look at the case of Rn. So in this case, the unitary dual and also this should be T, and the tempered dual, they are both Rn, which is the same as the previous space, and they are also known as the Pontryagin dual. And if we consider the Dirac operator on Rn, then we will have, because Rn has a symmetry, because the Rn group acts on the space Rn just by translation. So Rn has a very nice symmetry, and under that symmetry, there is a index in the K-theory of the reduced group system algebra of Rn. And this reduced group system algebra under the Fourier transform will be transformed into from convolution algebra to C0 of Rn just by the Fourier transform. And this gives rise to isomorphism between reduced group system algebra of Rn and with convolution product, and C0 of Rn with just the pointwise multiplication. And this system isomorphism induces an isomorphism on the K-theory level. And if we look at Kn of C0 Rn, that will be isomorphic to Z. And we would like to we would like to see how does the equivariant index of a Dirac operator on Rn transformed into a K-theory of C0 Rn. And the proposition we want to show is that this higher index in K-theory of the reduced group system algebra of Rn transformed under the Fourier transform into the Bott generator of Rn. And I will kind of show two methods of understanding this Fourier transform. So first of all, let us not assuming we know anything about the Hilbert C star module that's the exon. So let us say we have a Hilbert C star Rn module, which is constructed by just completing this C infinity function, C infinity sections under some reduced group system algebra valued inner product. So suppose we know we just know this information, and so let us think of this. Yes, I will talk about that later. But so this operator D is can be lifted to this Hilbert module over C star Rn. And we would like to look at the transform. So we will try to find the Fourier transform for this space, EG, and also for D separately. So so the claim is that the Fourier transform of this space, which is a Hilbert C star Rn module, will be transformed into a C0 function of Rn taken values in a family of Hilbert spaces. But at this point, the Hilbert spaces are finite dimensional because this H pi stands for the irreducible representation of Rn. So they are all one dimensional, and this S is just spinor bundle over Rn. So this lemma claims that under Fourier transform, this Hilbert C star module just transformed into some C0 function on Rn taken values in a family of finite dimensional Hilbert spaces. And in the meanwhile, the Dirac operator will also transform into a families of operators parametrized by the tempered representation of Rn, and that is just Rn. And being differential operator on E, it will be transformed under Fourier transform into multiplication operator by the Clifford multiplication. And that is the lemma. And our way of proving the lemma is trying to include this Hilbert C star module into a free module. That can always be done by the so-called Kasparov stabilization theorem. As long as this Hilbert C star module is separable, we can always, so for any Hilbert C star A module, we can always embed that into a free module, which is of the form of a Hilbert space tensor, the C star algebra. And here, we can have a very explicit embedding, but I didn't write it down. We can have an explicit embedding of this very abstract space into C star Rn tensor L2 sections of Rn. And we can define and also the action on this larger space by the Dirac operator will be replaced by one tensor D. Why is that? Because as I said, this C star algebra valued index is essentially some family index. So so in the direction of the algebra, there should be no action. It's like family index. If you have a family of manifold over some base, you will have Dirac operators on each fiber over this base, but there will be no differentiation in the base direction. And here, this C-star algebra picture, C-star module picture is that we replace this base by an algebra. And in this case, it's commutative, so it's still a space, corresponding a space. And there should be no differentiation along this direction. So the action should be when tensor D. But in any case, we will apply Fourier transform. Instead of applying Fourier transform on this smaller space for D, we will do the Fourier transform on this larger space and for this one tensor D. And over this larger space, one can define the Fourier transform of a function here to a function here. And for D, because with respect to the first, the algebra part, there's no operator acting. So on the dual space level, the Fourier transform of D only works on this L2 space. So the property of the Fourier transform implies that it will transform a function, differentiating a function into multiplication by an operator on the dual of that function. And this multiplication only happens on this part, not on this first part. So in any case, yes, by an easy exercise, because Fourier transform maps partial derivatives to just multiplication of, so Fourier transform of partial derivatives will be transformed into Ixii. And because Dirac operator is a linear combination of partial derivatives, and one can easily show that this d pi must have this form of I of Clifford multiplication by a vector, and this vector psi lives in Rn hat. Yeah, so this is how d pi acts. Okay, so the formula for the.
Can I ask a silly question? This Clifford multiplication was a symbol of the Dirac, right? Is that right?
Clifford. Yes.
Does this Fourier transform always takes you to the symbol of the operators? Is that?
No, it only works for constant coefficient differential operator. So if you have a differential operator where the coefficients are just constant, then the principal symbol is the Fourier transform. If your differential operator has a coefficient, for example, x times ddx, then when doing the principal symbol, you freeze the coefficient, and you do Fourier transform only on the partial derivative.
I see.
But if you do Fourier transform to this whole thing, it will be something different.
Okay, thank you.
But in this case, the Dirac operator has a constant coefficient, so it is okay. In any case, the formula for the Fourier transform for the D action is simply given by the Clifford by this Clifford multiplication. And this Clifford multiplication only happens on the L2 part, only on the L2 part, which is this part, but not on this part, because on this part we don't have any D action, because on this part we have the operator 1 here. It doesn't do anything. And how to understand how to restrict this operator to this smaller space? Well, one have to regard this space as in here, C star G, tensor, and doing Fourier transform here will give us right. And if we only restrict the Fourier transform to this smaller space, then it can be shown that the image of this space under the Fourier transform will be transformed into this family, this C0 function in this family. So this family will different when you choose different point on Rn hat, but this space with coefficient in a family of Hilbert space can be embedded in a larger space. In any case, if we only restrict this operator on this pi, then we will have an operator on C0 Rn, where on each pi inside the dual space of Rn, it will Clifford multiply this pi vector on this spinor bundle. So by definition of the Bott element in the KK theory language, this is the generator. This is the Bott generator. Okay, so this seems very complicated, but in fact, there is another point of view of this, which I'm going to use in the context of complex semi-simple Lie group. Actually, we don't have to embed that EG into a larger space. One can just work directly on the Dirac operator on this L2 sections. And because in this case, this spinor bundle is just trivial, so I just take, I just rewrite this L2 RNS into L2 Rn tensor a spin representation. And one can just either view this Dirac operator on this L2 space by, so this L2 space can be either viewed as a Hilbert space, but it can also viewed as Hilbert modules over C star Rn. So one can actually just take the Plancherel decomposition of this Hilbert space, L2 Rn, and perform a Fourier transform D on here, see what happens on here. Yes. So the differentiation operator here will, in a similar way, transformed into a multiplication operator, a family of multiplication operator over parametrized by this tempered dual of G, and the as we shown before, the Dirac operator will be transformed into Clifford multiplication. So this d pi acts on delta by Clifford multiplication. And in our setting, this h pi, they are just dimension 1. So this family of operators, d pi, they are just this family of operator d pi, each of them, they are just given by some represented by a finite matrix. It's a linear transformation.
So
And
the composition happens because Dirac commutes with the G action, right? The regular representation. Is that the point here? That you can restrict it to individual these, what you're summing over.
right, yes.
Okay.
Yes, because this Dirac operator commutes with the G action. So one can restrict the Dirac operator to each component h pi, and it doesn't change.
Thank you.
Okay. In a similar fashion, one can just see this d pi is given by just Clifford multiplication and hence the Bott element. But there is some slight issue here because because maybe it's not correct to use L2 here. But I need to think about it, because if we use L2 and the Plancherel decomposition, and actually the dual space should be L2 Rn hat instead of C0. But here I'm just omitting that issue. So if I find a way to find a good replacement of this L2 thing, I will change the slides later. But throughout today's lecture, I'm going to work on this L2. Okay. So next I'm going to talk about the case of the complex semi-simple Lie group. A typical example we are going to refer to a lot is SL2C. Okay, and the problem here is that we would like to find the precise image of the Dirac induction. So we need to pick an element in RK, and that is sufficient to just look at an irreducible representation of K. And let us assume this irreducible representation of K is labeled by its highest weight, which I call tau. And the problem here is that we would like to find the Dirac induction, the image of the Dirac induction of this representation in RK. And this should be V tau. And the general strategy, as in the case of Rn, is to write this equivariant index as a KK element. So just as a reduced group C, so just as a C star reduced G module, which is this one, acted by the twisted Dirac operator. And we would like to apply Fourier transform to C star reduced G, to this C star G module, and to this Dirac operator to see what is happening on the dual side. Okay, and actually that calculation will give us this theorem by Pennington-Plyman, which says that for complex semi-simple Lie group, the K representation represented by the K representation labeled by the highest weight will be mapped to the component of M hat with the highest weight tau plus rho K. So probably I need to recall what does that mean. So in the case of SL2C, G hat is A hat times M hat over Wang group. I mean the tempered dual. And in this case, it will be just a bunch of lines together with a half line. And each of these lines, they are labeled by sigma inside m hat, where m is a circle, so m hat is z. And because K-theory of this group system algebra is just the topological K-theory of this space, and one knows that K1 of each of these lines gives rise to a generator. So we say that the K-theory generator is just labeled by this sigma. So that is what we meant about a component for sigma, because each sigma corresponds to a K-theoretic generator. Okay, so let us before the detailed proof, let me say something about the general strategy. So now we need to work with one component of a family of irreducible principal series, and first we are going to decompose the reduced group system algebra using Fourier transform, and that is for that we will refer to the lecture by Bram. And then we need to use Fourier transform to decompose this space by applying the Planck-Rail formula for L2G. And then after that, after we know what are each component of this space, one can restrict D to each of the space and study the behavior of D applied to each component, each component in here. And that is the process of Fourier transform of D at each point in the tempered dual. And it is very important to study the properties of D pi. Here, D pi just means the form of D restricted to the pi component. So that is D pi. And some important properties of D pi is the square of D pi is scalar multiplication. And that would be useful for us to conclude that D pi is a Clifford multiplication, because Clifford multiplication has the property that the square of that is a scalar multiplication. So this is a rather important property. And also an important property is, when does this D pi invertible? So if D pi is invertible, and that is equivalent to say D pi squared is positive, because D pi is a self-adjoint operator. So this is important because we can tell if the component for D pi, if the K-theory component represented by D pi is 0 or not. If it is 0, then we just discard this component. It will simplify the calculation a lot. So if some operator is invertible, then the index would be 0, because the index is an abstraction of an operator being invertible. So if some operator is positive, then we know that D pi does not contribute to the equivariant index. That is important.
Can I ask you questions?
Yes.
Do you need the H pi instead of L2G here?
H pi?
Aren't you restricting D to the component of pi in the decomposition of L2G? This L2G...
Sorry, I don't understand the question.
So D pi acts on H pi times spinor times V, no? K points of...
Yes, I will say it precise later, like that, yes. Yes, D pi acts on a decomposition of H pi inside L2G.
But then why is this last point that you say is finite dimensional? Is it finite dimensional with the full L2G? I got.
Oh, I see what you mean. Yes, that should be H pi. Yes.
Am I right?
H pi.
Yeah.
H pi. Sorry. H pi.
Yeah. So yeah, and the point here is that d pi square is essentially the Laplace Casimir and Casimir x by the by a scalar on the irreducible component. That's why it's scalar multiplication, right? Yeah. Okay.
Yes. Some it's Casimir plus something else, but yeah.
Okay. Okay. Thank you.
Thanks for the correction. Yeah, if you replace L2G by H pi, then one can see that this d pi is actually acting on some, this space is finite dimension, and it will, even better, it will vanish in many occasions, and that will make the make only one component inside the K-theory generators stand out. So given an irreducible representation of K, and we can find only one generator inside the, how to say, so given a representation of irreducible representation of K, one can just locate exactly one component in the K-theory generator to correspond to that. We will see. 8. Okay. So let us now doing the calculation step by step. First of all, let us decompose the reduced group system algebra of G. So for a complex semi-simple Lie group, the nice thing about this is its tempered dual is a Hausdorff space, and the reduced group system algebra can be written as an isomorphism with C0 of tempered dual of G with coefficient in compact operators. And being more precise, this tempered dual of G, I'm sorry, this should be W, is the form of M hat times A hat over W. And it and we can actually restrict this W to each component, by which I mean the A hat component labeled by M hat, because A hat here will just be some R to the N, and M hat will be discrete. So this space always looks like some A hat component over M, but dividing this Wang group action, the component will either look like just A hat if the Wang group localized to one component is trivial. So we either have a full A hat, or we have A hat divided by some finite subgroup, some subgroup of the Wang group. So in the example of SL2Z, sorry, SL2C, it will be each component will be mostly just R, which is A hat, but only one component has this form, which is R divided by Z2, reflection by Z2. But in any case, we will denote this each component associated to an irreducible representation of M, which I call sigma, by C sigma. And we will rewrite this isomorphism as a direct sum over C0 function over this each component over M hat, taking coefficient in compact operators. And this sigma is over M hat divided by W. So M hat in the case of SL2C is just Z, and m hat divided by the while group action is just a positive, non-negative part of z. Right. And that corresponds to these component. They are just labeled by non-negative integers. And also, coming from Ram's lecture, this H sigma is a family of Hilbert space. H sigma is a family of Hilbert spaces over A hat. The construction is given by the parabolic induction of C0 A hat V sigma. And here, V sigma is the representation space of sigma. And C0 A hat V sigma will be a representation for A hat times sigma. And sigma belongs to M hat. So we can do parabolic induction. And also, I would like to mention that this family of Hilbert space, they are consisting of all tempered irreducible representations labeled by sigma, but the A factor is changing. So in other words, we are fixing sigma and letting the A hat parameter changes, and we can produce the parabolic induction, and we call that pi sigma lambda and H with the representation space H. And if we take the direct integral of this representation space H sigma lambda, integrating over lambda, then we recover this family of Hilbert spaces H sigma. In any case, I'm just saying this H sigma carries the information of the irreducible representations of G, which is labeled by sigma. Okay. This is the decomposition for C star G. And next, we are going to look at the decomposition for the space. Okay, so we are applying the Plancherel decomposition, which is so L2G splits into H sigma lambda tensor H sigma lambda star over G hat, and I'm doing it component wise, so it's over C. Sorry, it's C sigma. Okay. And because this space, how to say? So because this H tensor H star, it's acted on the left by G and on the right by K. So actually, this K action does not do anything on the first component. So we can rewrite this thing into this form. So we only need to find the K invariant part of these three tensors. And the lemma, important lemma is to conclude that this K invariant space has finite dimension, and moreover, it will vanish for. I shouldn't say it has finite dimension at most of the cases, and also it will be zero among those cases, but one. And the lemma says that if sigma and tau differ by the half sum of compact roots, then the dimension is 2 to the half dimension A, but we take the largest integer below that number. And if this tau plus rho k minus sigma does not belong to the positive while chamber, then the dimension would be 0. And I would like to say some idea about the proof. So let us denote WA, the irreducible representation of K with highest weight A. And by Frobenius reciprocity, one can obtain that the restriction of H sigma lambda to K, and H sigma lambda is just this parabolic induction. One can just, when restricted to K, it is the same as you just restrict G to K and then take the intersection of P with K, which gives you M, and simplify this into just inducing this sigma. So in any case, this equality tells us that when restricting this parabolic induced representation to K, it will be consisting of it will be decomposed into irreducible representations of K according to their weight, and the irreducible representation with the highest weight is with sigma, and all other irreducible representations has weight that is has lower than that. And also, how does this rho K comes about? It comes about viewing this spin representation as K representation and split it into direct sum of irreducible representations, and of those with the highest weight, that is just rho K. So that is how rho K comes about. And this number comes because this highest weight representation, they have multiplicity of this number. And for V tau, it is just, by definition, V tau is irreducible, so it's just W tau. And using Schur's lemma, one can show that the dimension will have this property. Okay, with that preparation, we will also look at Fourier transform for the Dirac operator. So the Fourier transform will be transformed according to this rule. So the restriction of D to the sigma lambda component will be denoted by D sigma lambda. And it is a very important lemma saying that the square of the Dirac operator twisted by this K representation, but restricted to sigma lambda component, the square will be a scalar, and the scalar multiplication is calculated by the information using sigma, lambda, and tau. So it involves all the three informations involved on the left-hand side, and also another compact root information. And this lemma is non-trivial because one has to use Pythagoras' formula for computing this square of Dirac operator on G mod K. I'm not going to review the proof of this lemma. So what can we observe from this lemma is that if tau plus rho K minus sigma is belonging to positive Weyl chamber, that means this number will be larger than this one. Then that will tell us that the square of this restricted Dirac operator will be positive, hence it is invertible. So this will be used to show that for this situation, the Dirac operator does not give any K-series generator. Okay, so for this, using this corollary and the previous two lemmas, we can do a simplification in the following. So previously we have done the Fourier transform to C star G, D, and the space, and they will be decomposed into the following form. Okay. And this following form is actually a direct sum over sigmas, because the k-theoretic components, they are labeled by sigmas. So it's actually a decomposition into direct sums. And one need to find what exactly the number, what is exactly the thing in the direct sum. And it turns out, using the previous two lemma, there's only one thing survives. That is, only when this sigma is equal to tau plus rho k, that component will survive. Other component will vanish. Because if sigma is larger than tau plus rho k, then we can use this corollary to conclude that the operator is invertible and it doesn't give you any k-theory generator. And if this is negative, then we can use this lemma to conclude, if this is not positive, we can conclude that the dimension is 0. So with those two lemmas, we see that only when the component, the sigma component, satisfy this condition, that will survive. And moreover, we need a further lemma to conclude that when sigma satisfy this condition, this component is actually a hat. It's not a hat mod some non-trivial finite group. And that is following from this lemma. Yes, this lemma says that the component for sigma in K-theory is not 0 if and only if sigma has the form, the highest weight of sigma has the form tau plus rho k. This not only tells us that C sigma is a hat, this also tells us that for any K non-zero K-theory, for any K-theory generator, it comes from some sigma of this form. So this also shows it search activity. Okay. So now our calculation of this equivariant index only reduces to this one component. So the difference is that we have now replaced all sigma by this tau plus rho k. And we also replaced that C sigma by a hat. And one need only to see, to show that this operator gives you the generator, which is the Bout generator. And to see that, one need to use the dimension condition on this space. We see that the dimension condition of this space is very similar to the dimension of a spinor bundle over Rn. And in fact, because of that, I'm going to denote that by this S to mean it is some spinor representation. Of course, this S depends on these things, but it has the same dimension. Okay, so then one can understand this restricted Dirac operator. I'm sorry. Actually, this restricted Dirac operator as an endomorphism on this H tensor S. Okay, and this is an endomorphism as C0 A hat with coefficient in K modules. This is because our cycle is in K theory of this one, and regarded as a KK thing, it is a module over this algebra, and that means this operator, restricted operator, must commute with some the compact operators, and that means this restricted operator must have the form one tensor sum operator here, because if it has some if this part is not 1, then it won't commute with these compact operators on the Hilbert space. And next, we use the fact that we can calculate this square of the restricted operator, and we are only considering the case where sigma is equal to tau plus rho k, and in that case, we just have lambda norm squared. So we have the restricted operator squared is just the norm of lambda squared, and use the finite dimensionality of this space and the form of this D, one can easily conclude that this is just one tensor I Clifford multiplication. And we can regard A hat as some Rn. So we have one tensor C lambda on this H tensor S, and we need to do a further reduction by removing this part, and that is due to Morita equivalent, because the left-hand side belongs to the cycle KK C0 A hat K, and this compact operator acts on the first on this Hilbert space, and this simplified operator belongs to KK C0 A hat without this K coefficient, and it can be proved that they are the same thing under this Morita equivalent. So under this Morita equivalent, we can remove actually this first part, and so this is simply a field of spinor representations over A hat, and the operator is given by the Clifford multiplication. So that concludes the proof, because this representation indeed gives you a generator. I hope this is fine. Okay, so I have a few more slides on SL2R, but very briefly. So I will talk about discrete series in SL2R. And let us recall a most general form of connected real semi-simple Lie group for the reduced group system algebra due to Wasserman, and later in a more complete sense by Clare, Crisp, and Hickson. It has this decomposition as explained in Bram's lecture. And in the case of a discrete series, sorry about this mistake. In the case of a discrete series of component, the cuspidal parabolic group is G, and this sigma would be a discrete series of G. And a discrete series component will just reduce this to compact operator, because there's no, the A star will just reduce to a point, and there's also no W sigma, I think. So discrete series gives a full generator for inside the K0 of C star G. And we want to look at what is, how to identify the equivariant index of SL2R with discrete series in a similar way by Fourier transform. So we look at representation of SO2, which is the maximal compact subgroup in SL2R, and it's labeled by weight N. And we consider Dirac operator twisted by that representation of K. And I will make a few claims. So for K not equal to 0, similar as in the complex semi-simple case, one can show that the principal series component of the image of the Dirac induction actually vanishes. What do I mean by principal series component? because for the case of SL2R, the K theory is already calculated like this. So it will be a bunch of countable family of discrete series generators together with one generator which comes from limit of discrete series. And this part is the so-called principal series component. And when K is not equal to 0, because this part is contributed from principal series representation, and one can work as in the complex semi-simple case to show that if K is not 0, this index will not land in here. We'll have no components from here. So that means the index will only land in the discrete part. And we denote Hn, we identify Hn with dm plus and minus. Okay, so in any case, under Fourier transform, the index will only land in the discrete series part, which is inside K0 of compact operator and taking the direct sum over the numbers when n is not equal to 0. Okay. And one can use similar argument as before, because we said that this operator acts on Hn tensor some other finite dimensional space. And this operator, because it is an KHN endomorphism, so it is an endomorphism over KHN, so it will have the form 1 tensor something, tensor sum m, and using the Fourier Morita equivalence argument, one can remove this K and remove this 1. So one can reduce that to an operator on some finite dimensional space in K0 of C. And because now we are working on finite dimensional space with an operator, and we would like to identify this thing inside K0 of C. That means we just need to calculate the Fredholm index. But the Fredholm index of an operator on a finite dimensional space is just given by the difference of the dimension of the domain and the image. How to say? It's it's just given by the difference of these dimensions. And in this case, we have this Z2 grading. So I think there are some mistake. Delta plus, and this is delta minus. Sorry. And this will reduce the calculation of the index by a bunch of integers. And using the two magic lemmas showing most of these integers will vanish, one can actually see that only when n equals to k, these are non-vanishing and equal to 1. And for all other component, it will be 0. So in this case, we show that the equivariant index associated to Vk, where k is non-zero, will correspond to a discrete series representation labeled by k. And that is about discrete series representation. And the thing I haven't talked about is how to identify this limit of discrete series component with this limit of discrete series component with k equal to 0 representation, k representation. I wanted to do it in this lecture, but it turns out I cannot find a precise reference for that. So I would refer to two things. One is this Brodsky, Niblo, Plyman, Wright's paper. That is not about SL2R. That is about universal cover of SL2R. And in that paper, they calculated using the Fourier transform, what is the K-theory for that group. And that is very much related to this case because in the universal cover of SL2R, that generator, we only have one generator for K1 group, for the K1 group, and that generator is the same as this one. So I believe in their paper, in this using the same technique of the Fourier transform, this can solve this problem. And also in some upcoming paper by, I think it should be by Claire, Hickson, Song, and Vaughan. They have used the Vaughan's minimal K type to show, also plus the Fourier transform to show Concaspar isomorphism. So that will also include this complicated case. Okay, and I want to mention a few other approaches which I have no time to say. One thing is what I omitted yesterday, the Dirac method. And another thing I found very interesting is an approach of showing Concaspar isomorphism is from a talk given by Xiang Tang, I think 3 years ago in Oberwaffe. He and Hickson and Song, they claimed that they can create some modified orbital integral. And in any case, it is some trace on the C star G, and that will be deeply related to the character formula for G. And they can use this trace to create a function on the T, which is the Cartan subgroup of G, in the case of when G has discrete series. And they can show that as a function T, it is the character value, it is a character value of some K representation. Actually, it is some function on T invariant under W, which gives you a K which is given by the character of some K representation. And I think that is a very interesting way of showing the inverse, showing the surjectivity of Concaspar isomorphism. But I haven't seen a paper comes out of that. And also another approach, but which may be also known, is that working with actually projections, not projection unitaries instead of KK theory. So in the approach I was talked about, it is all about KK cycles. We work on Dirac operator on some module. It's not so explicit. So people want to work on just precise projections in K theory. The reason is that the projections in K theory can be actually given by matrix coefficient of discrete series. So matrix coefficients of discrete series, they give a projection, precise projection in the reduced group system algebra. And one want to identify which higher index, which equivariant index will be attached to that. And this equivariant index can be geometric. And it is folklore that using some heat kernel method representing this index and letting the time variable tending to infinity, that will converge to some matrix coefficient of some discrete series. But I haven't seen any paper out of that. I just hear that is possible. Okay, so that is everything I want to say. Thanks a lot for your attention.
Thank you, Han. All right. Any comments or questions? I should say it while I still on my mind. I don't think it's what you're referring to with the heat kernel, but there's an old paper of Valette which actually identifies, works with projections of the discrete series representations and stuff. It's quite explicit. It's a very old paper from '84 or something. It's like with a typewriter kind of.
It's not that paper about one Catan group.
No, it's before that. It's around the same era when he was really into this stuff. I don't.
Okay.
I asked him for a scan. He sent me a scan of it. So it's. I don't think it's available around. But yeah, it's. But here's another paper with the projections. But it's not fully what you're saying. It doesn't try to identify it with these index G theta with heat kernel, all that stuff. It's not there. But some part of the using projections to get to the right hand side from the matrix coefficients is there. Yeah.
Okay. Thanks.
Yeah. So this trace that's supposed to be inverse, huh? For the
right.
Concast.
I think this is a very interesting point of view.
I heard about that too in a talk of Song, I think.
Yes.
I think Peter might be involved in some aspect of it. There are a couple of collaborations, I think, but I think Peter also worked on that orbital integral that Xiang and Yan Li Song created.
With the index theorem from that, you can show that the reconduction is injective, but I think surjectivity is more complicated.
Any comments or questions? Presumably, once we have the description, computing the K-theory of it is also could be done in the p-adic case, right? If you have the description of as a group C-star algebra, it looks very similar, right? We have C-naughts on some parameter spaces with coefficients and some compact operators on a finite dimensional space or something like that. So probably the Fourier transform.
Yes, but in p-adic case, I'm not so sure about Dirac operator. Maybe there is a replacement.
Yes.
Okay, so you need, but
maybe there is a replacement.
I see. So you don't have the good old Dirac induction there, what is supposed to
Yeah. Could I just say something here? Yeah, that is a sort of long-standing conundrum, what the Dirac operator can possibly be. Sometimes it's simply zero, so that the kernel of the Dirac is a compactly induced representation, which, with a bit of luck, is irreducible. But there's also the simplicial Laplace operator on Euclidean buildings. There's something called the simplicial Laplace operator. Now its L2 kernel realizes either the Steinberg representation or generalized special representations, as Anne-Marie has indicated. That might be a clue that somehow there is a Dirac operator on the Euclidean building, and its square is somehow related to the simplicial Laplace operator, which is a well-defined object on the Euclidean building. There might be some possibility in those ideas, but they've never been really pursued, that kind of idea.
I see. So the simplicial Dirac is just kind of an averaging over the neighbors, right?
Yeah.
And it's actually like a Hecke operator with index P. And the idea is to find the kind of a Dirac correspondence.
There's a famous paper by Borel where he looks into this, the L2 curve. Well, you see there's a remarkable, at least superficially, there's a remarkable analogy between L2's, the L2 kernel of the Dirac operator on the one hand, and the L2 kernel of the simplicial Laplace operator on the other hand. Each of them creates elements in a discrete series. So that there must be some potential in that point of view.
Interesting.
That problem is up for grabs. So if anybody feels like pursuing that, there's bound to be something there.
It looks like we should come up with a open questions file out of this summer school. Maybe, yeah, it looks like there. You would think that everything, these are the foundations, everything is completely mapped out, but there are some like
Not far from it, far from it, far from it, far from it, far from it.
All right then, let's thank Hang again. Thank you very much, Hang.
Thank you for this opportunity.
Oh, thank you. This was very informative. Right, so let's see. We have 12 minutes before continue with Anne-Marie. So let's give a 12-minute break and continue with Anne-Marie. Okay, so, oh, yeah, stop the recording.